In this video, we're going to handle gas stoichiometry problems which involve the collection of the gas over a liquid. Right, imagine a setup like this one where you have a reaction flask and a gas is going to be generated. Okay, the gas then is going to go through this column, and then what we have is that we're collecting that gas over liquid water. Okay, so the gas is going to bubble up this tube until it gets to this part here where you're actually going to have the gas collected, and you can measure the volume that you're collecting. Right, so let's actually then do a numerical problem to illustrate some of the challenges associated with this method of measuring the gas generated in a chemical reaction. The work that we're going to do, the problem is going to be dissolving brass in hydrochloric acid. So in that flask we have hydrochloric acid, and then we're going to add a piece of brass which weighs 200 milligrams. Okay, brass is an alloy between copper and zinc, and then what happens is that the reaction that we have out here is zinc reacts with hydrochloric acid, which is an aqueous solution, to generate zinc chloride plus H2, which is a gas. Okay, so this is the gas that is generated in a solution. Is a highly flammable gas, hydrogen, right? So it's useful to actually collect it carefully in a setup like this. All right, so we have some data in the problem. What we have from the statement is that the volume of the hydrogen gas collected, the volume is equal to 14.95 mils. Okay, we have that the pressure at which that gas is, that pressure happens to be equal to 752 torr. Okay, the temperature is 25 Celsius. And the problem is also giving us that the, something that is called the vapor pressure of oxygen under those conditions happens to be 24 torr. And the question is, well, how much of this, with this data, calculate how much of these 200 milligrams of brass is actually zinc. Okay? Copper does not react in this fashion. All right, so the most striking aspect of this problem is that you have here, actually that is not correct, that is the partial pressure of water, not oxygen. That's just water. Okay? This is actually the most striking piece of data that we have in the problem. And here's why that's striking, right? Or why that is important. It turns out that every liquid that you have, okay, suppose that we have here a container with water, okay, this water is in the liquid phase, but there's always a few molecules of water that are in the gas phase. This is actually due to entropic effects, and that's something that we'll learn later on. But it turns out that again, there's some water molecules in the gas phase right here. This is what we call the vapor pressure of the liquid. Okay? This depends on the temperature, so if this water is hotter, then you have a larger vapor pressure, and it also depends on the liquid, right? So for example, if you have something like ethanol, which is more volatile than water, then the vapor pressure at the same temperature would be much larger for ethanol than for water. Okay, so this is what the problem is providing. This complicates a little bit our problem, because what you actually have right here is not only the H2 that is generated from the reaction, but also a little bit of the water, right, due to the vapor pressure of this liquid. In the end, you're collecting this gas over liquid water, so again, you're going to have some gas molecules of water right there. Okay, so then our goal is going to be to just determine exactly how many moles of hydrogen we have right here, then utilize here stoichiometry to go from the moles of hydrogen to the moles of zinc, and then we don't have the moles of zinc, we know the molar mass, we can generate the mass of zinc, and then calculate how much of the brass is zinc. All right, so let's try to figure out what the moles of hydrogen are. Notice that we can actually use the ideal gas equation here, okay? And here that will be the number of moles of hydrogen. Now, the only problem with that is that this pressure that we have to plug in there has to be the pressure due to hydrogen, not the total pressure. And the problem is actually giving us the total pressure. That is the pressure of both hydrogen and water, right? So the pressure of hydrogen can be straightforwardly calculated using Dalton's law. But the total pressure that we have here of the gas is equal to the pressure due to the nascent hydrogen from the reaction, and then the little bit of vapor pressure of water. Okay, plugging in the numbers here, that will be 752 torr is equal to the vapor pressure of hydrogen plus 24 torr. Right, so you can see how the contribution of the water vapor pressure to the total pressure is quite small, but if you want to do this accurately, then you have to consider it for sure. All right, so when you do that math, this vapor pressure, not the vapor pressure, but the pressure of H2, or solely due to H2, happens to be 728 torr. Okay, so from here we actually have everything that we need in order to be able to solve for the number of moles of hydrogen, right? So the number of moles of hydrogen is going to be equal to the pressure of hydrogen times the volume over RT. All right, again, we have everything that we need right here. All right, so let's then crunch the numbers. These are, we're going to be using here is 0.08206 atmosphere liter over mole Kelvin. Okay, notice that the unit of pressure there is atmosphere, and the unit of pressure that we have here for hydrogen happens to be in torr. So we're going to need to transform those torr into atmospheres so that we can actually have cogent units in this equation. Right, so let's work through this carefully. Right, we know that the pressure of hydrogen happens to be 728 torr. The conversion between torr and atmosphere is 1 atmosphere is the same thing as 760 torr. You'll have to multiply by the volume, which is provided by the problem. Notice that this is milliliters and we need liters. So that happens to be 0.01495 liters. Okay. Then we have the R, which we have already written here, multiplied by the temperature, which is 25 Celsius. That happens to be 298 Kelvin. And from here, you actually get directly the number of moles of hydrogen. Okay, so that is going to be 5.86 10 to the minus 4 moles of hydrogen. Okay, so we're actually now ready then to do the stoichiometric calculation. From the moles of hydrogen, we can find the moles of zinc, and then from the moles of zinc with the molar mass of zinc, we can get the grams of zinc, and then figure out what is the percent composition of that brass. All right, so let's work that out right here. We get that 5.86 10 to the minus 4 moles of hydrogen. We cross the stoichiometric bridge, and we have 1 mole of zinc for every mole of hydrogen. That will give me moles of zinc. Now I multiply by the molar mass of zinc, which is 65.38 grams. Grams of zinc for every 1 mole of zinc. And this is going to give me the mass of zinc that I have in that brass that I threw into the hydrochloric acid. Okay, so this number happens to be 3.83 10 to the minus 2 grams, which is exactly the same as 38.2 milligrams. And again, this is zinc. Okay? Well, so then we can actually then figure out how much of the brass is zinc. Right, the total mass of brass is 200 milligrams, and the mass of zinc is 38.2. Most of the brass happen to be copper, right? Very little is zinc. We can take the ratio of these numbers, multiply by 100% to find out that 19.2% of the brass happens to be zinc. All right, so in this video we have explained the collection of gases over water and how you can use that concept to carry out stoichiometric problems involving those gases.